I think it's lower than that.
Just like
actually, I heard it.
he like sees the distributions.
It probably was.
Okay, folks.
Yeah.
Welcome. Actually, one more than is all So, you don't know who I am? That'd be me. You're welcome to use that for my name. My office is Long Hall 205, and my hours this semester are 7 to 8 a.m. Monday, Wednesday, Friday. That really probably like 7:45 or such because I've got my 8 o'clock. 10 to 1 p.m. Wednesday and 10 to 2 p.m. Monday, Friday. That's a lot of office hours. I hope that accommodates you. If not, please let me know. And you know, if you're that type of person, I can come in earlier because I'm usually here about 5:30. But anyway, let me know if that's a problem. My email, you probably all know because you get math club mags from me just incessantly. So let me say a couple things about the syllabus, which is posted online, but I do like to say a couple things about it. So in this course, the way I grade it, you will have homework. You should count on them being once a week, but less than once a week, but you should count on being once a week. And I do have a homework due this Friday, but it is pretty easy. I don't know if you've looked at it. It basically, I just asked, what's your math history? What do you want to get out of this class? It's just kind of a get to know you kind of thing. So turn it in and get a 1, you know, say something funny, whatever, doesn't matter. So the homework average will be half the grade. If you haven't had me before, I've got a grader in this class, and the homework problems will be maybe some of them 3 problems or points, some of them 5 points, something like this. I'm going to tell the grader to grade harshly, as I always do, because I don't want you getting 5 out of 5 or 3 out of 3 and say, oh, I did this perfectly, and there's subtle problems in there. I would rather address that in the homework and slash you there and have you learn the stuff. Because of this, your homework average will be curved around a pretty benevolent mean. So if you're in the middle of the pack, you're probably getting at least an 80. However, I like to be very transparent. At any point in the course, you can ask me, do not trust numbers that Canvas generates. It's crazy. But at any point in the course, you can ask me where you're at, and I can tell you because I run this kind of running average for the homework. There'll be 2 exams. Right now they're scheduled for February 11th for the first exam, which is Wednesday, and then, no kidding, April 1st, which is also a Wednesday. And the final exam will be, it's Friday final exam with the registrar schedules. The 2 midterms will be worth 15%. Final exams worth 20. But the homework, I think, to me, the homework is really the linchpin of this course. And I can see very happily that most of you know each other because you're all talking about it here, which is good. If there's anybody in here that feels like they're not in that set of people that know other people, change that, right? Look around you. This is the best resource. These are your best resources. All right. So I highly encourage you to work together on the problems. Come holler at me in office hours if you're having difficulties, but yeah, work together, get to know each other. You all are going to be colleagues maybe years from now. And I do say my little bit about AI, which I keep moving up the, oh yeah. The grades, the 90, 80, 70, 60 scale. And once again, here's the 3190 review. It says in my syllabus, if you get a 90, you will get an A. It does not say if and only if. Now, you need to live it like it's only one direction. That's the best way to live your life, right? But at any point, again, I'll kind of see where I think you're at, kind of thing. I do not require attendance in this course. You all are all adults. But for the love of God, come to class, please. It really covers a multitude of sins. It'll make your life a lot easier. However, I realize that, you know, sometimes things might happen. You might get sick, who knows what else. As technology permits, I record the lectures, as I'm doing right now, and I will post them on campus and on my YouTube channel, so you can watch them. Right. And I want to say something about, oh yeah, the policy. Yeah. Okay. I'm not really too worried about this class that much, but I highly discourage the use of AI. But, you know, I'm not going to like pop up in your dorm room and check to see if you're doing AI or not. I mean, I just, you know, you're adults and I got, you know, I don't have that kind of time on my hands. Other Clemson students are a much better resource. And of course, as you know, you might play with AI just for fun. It's crazy the garbage it gives you. It gives you good stuff and it gives you garbage. And you can't ever tell the difference because it always acts like it's good stuff. Ooh, here's the answer. Yeah. So be super careful with that. It's very easy to not learn stuff by doing it that way. So what my policy is about working together on I highly encourage you working together. I highly encourage you avoiding AI as much as you can. If I or if the grader grades your paper and thinks that there's a problem where you have leaned too much in the grader's judgment or in my judgment, where, okay, this person's leaned too much on their colleagues or leaned too much on AI because I want to read what your take is on the problem, then you will get a 0 on those problem or problems. However, I realize that I and the grader are imperfect, so there's an appeals process. If you get a 0 on any problems, it means that, you know, well, it can mean two things. It means you didn't do the problem, or it means that, okay, we think you stepped over a line here. The appeals process will be from 1 week when you get the grade, you come to my office and I will give you a whiteboard marker and you can explain the problem to me, right? So that's the appeals process. Oh yes, and no, so I've taught this course an Avogadro's number of times, but not at the undergraduate level at Clemson. And so what I've actually started to do is you all have lecture notes up there, and they should be, they might be a little incomplete because time allowing me, I think I'm going to add a section on symmetric forms and determinants or something like that. We'll see how it goes. But basically the notes are what I use at the graduate level, the ones that you're using. So you would start on the notes that are posted on my webpage, posted on Canvas on, I think it's chapter 12. It's whatever the modules chapter is. That's where we'll start. But there will probably be some stuff that we skip over, or more properly, there'll probably be some stuff where we don't quite get into the weeds as much as I would for a graduate class. We're going to kind of see how this goes. Maybe we will, because I think I've got a good class in front of me. But anyway, that's about all I wanted to say about this kind of administrative stuff. Any questions about nuts and bolts or anything else? Yes.
Who is the grader?
The grader is Adam Price. Okay. So he's actually one of my grad students. Okay. Questions? All right. Yes.
Homeworks, do you expect them like typed or handwritten?
Oh,
Doesn't
yeah.
matter.
Okay. Yeah. I'm glad you brought that. So, no, I don't, but it's encouraged. So here's what I do. How many of you type in LaTeX or have done LaTeX? Right. Well, almost everybody in here. It's great, isn't it? I mean, you can really do some cool stuff. And I am an old-fashioned writing on the notebooks on the floor kind of guy. But when I got a little bit better at LaTeX, really, when I get a mathematical idea, I'll put it there because then I've got it. It's pretty easy to type and stuff. If you don't know LaTeX that well and you want to learn, this is a good opportunity to do it. the best way to learn anything like LaTeX is to steal. And I give you that opportunity because whenever I put a homework up there, I also put the LaTeX file that generated it. So if you don't know much about it, you can kind of look at the crap. And one of the best books I ever had about LaTeX way back when was like, it was like LaTeX for beginners or something like that. And literally there was no explanation. It was just one side was the code and the other side was an output. And it was just random stuff. And it was actually one of the most useful things. So that's why I think the best way is to steal. What I do want you to do is take a PDF of it. And this will be true for the exam too. Take a picture and upload. Please try to make sure it's of good quality. I like to be able to read it. That's another reason why I like LaTeX, because whenever I gives me some type, I can read it. But I want to, it should be, and please, this is another thing that happens with me. I don't want to open it up and have like, the letter E being this big. Some people do this, and I have to scroll 3 times just to read every line of there. Please try to look at the quality of what you put up there. LaTeX is encouraged, but not required. So, okay, other questions? Okay. So just for. So I'm curious, how many of you have had any experience with modules at all? You ever encountered them in your travels? Wow, everybody's module virgin. That's expensive. Well, this will be kind of fun, right? Because what are modules, right? How many of you heard the buzzword? Oh, it's an R module. Some very fancy saying. Well, so what a module is this is a generalization of 2 things: vector spaces and 2 abelian groups. Okay, everybody in here has had 3110, right? You remember back doing all that business with linear algebra, right? And you talked about vector spaces. Well, probably when you did 3110, I'm willing to bet in your book, you probably, when they defined vector spaces, they probably had like 18 things, right? It satisfies this and this. It goes through this huge long list of stuff, right? Everybody remember that? It's awful. No wonder people hate linear algebra, right? A good chunk of that beginning stuff is a vector space, first and foremost, is an abelian group. So if you forget about the scalar multiplication in a vector space and just talk about adding vectors and that's all you do, it's an abelian group because you have the 0 vector. When you add 2 vectors, you get a vector. You've got the negative vector, right? And so it's an abelian group, right? It's got this extra way that you can multiply things from a field. So when you took 3110, how many of you had a class where they talked about more general fields, or did they stick to it like it was all the reals? Yeah, so it's a mixed bag, right? But really the important thing about vector spaces is essentially what a vector space is an abelian group where you get the scalar multiplication. So what a module is, think of it this way. It's a vector space, but your scalars come from a ring, right? Not necessarily a field, right? So basically, it's an abelian group, and when you multiply it by a scalar, it's something that comes from a ring that's not necessarily a group. So that scalar that you multiply by may not have a multiplicative inverse. And actually, as silly of a small thing as that may seem, that actually kind of makes a big difference. I am going to usually focus on commutative rings, but I'm going to start off with a more general definition of what a left R module is. So let's kick it off this way. Definition. A left R module, and I guess I'll call this something like M, an additive abelian group. Which I will call M plus. So it's just some additive of this group. Equipped with a binary operation. From R cross M to M. And this is our scalar multiplication. It's often written R multiply M by this R, and you get this Rm, which is another element of M. That's the binary operation. Such that, and I want it, not just any binary operation, I want it to have a couple of nice properties. For all R, S in R, and X, Y in M, what do you think I want here? When I multiply a sum of two elements in the module by R, I want it to play nice. So I want it to distribute this way. When I take the product of R and S, which is another element of R times X, this is R times SX. Right? And I also want, remember R is a ring, and I want the distributive property to be good for the gander too. Notice this is exactly, in fact, if I replace R by a field for the real numbers, this is exactly what it takes to be a vector space. Right? Now, what do I mean by left modules? That means, so let me make a remark here. So the binary operation works this way, but perhaps right, it may not make sense to multiply the element of the module from the other side. Let me add to the definition here, and this is also, this is another assumption that's missing. You would have seen this next assumption. People don't generally make it, but we'll so this will be a default assumption. If I say module, you can usually assume unitary if I tell you otherwise. Also, if so if R has identity, so if your ring has identity and that identity then M is a unitary left R mod.
Dr. Bergman?
Yes.
When would the, like, the identity times an element not go to the element itself? Like, why would you define it not like that?
Well, I mean, you could, you could just define things by relabeling, right, in a certain sense, right? I mean, for example, you could take, you could take the even integers, for example, right? That's an abelian group under addition. And you can let your ring be Z, right? Yeah, I think that you could define some other action on there where the identity doesn't, times X isn't X. But remember, what you're doing here is on the surface of it, M is one thing and R is another, right? Tomato, tomato. So it's certainly true that the identity of R times anything in R leaves it alone.
Right.
But oftentimes what you're doing here is you're defining a multiplication. And to make the module unitary, you have to declare that the identity times anything in this new module just leaves it alone. So it behaves like the identity does in the ring itself, right? But ostensibly, you could change things if you like, right? But that's, most of our modules will be unitary, right? I mean, that'll be the default there. Now I said that a module is a generalization of a vector space, and I think that maybe from the definition, it seems like this is clear, right? Vector space, you can add vectors and subtract vectors. Now you can multiply them by scalars. So if R were just a field, I would have what I want, right, as far as vector space. I also said it's a generalization of abelian groups, and it is in a very profound way. So let me start this first example here. Example. Let A be any abelian group. Any abelian group that you could ever think of. By the way, when I say module, if I don't say left or right, I assume that it's what I call a two-sided module. And what I mean by that is when I multiply this, it doesn't matter what side I multiply the scalar by, I get the same answer. I could define a right module the same way I did, except I put the scalars on the right instead of on the left. Most of my modules, after we get the truck going, most of my modules will be modules. It'll be over a commuter ring with identity. Suppose I walk up to you on the street and give you any abelian group. Then this thing is always a module over what ring? Right now?
Identity.
The abelian group with trivial multiplication.
I don't think I could answer. I don't think I could argue with you, Todd. Put that in there for sure. What's the most basic ring you can think of? Think about it. I'll go over here and catch a few Z's. Right, there's one of them. Any abelian group is a module, is a Z module. Suppose I have a positive integer. What do you suppose n times a would be? How will we define this? Yeah, just add a to itself the prescribed number of times. Agree. Zero times any a is the zero element of the group A, right? And what about if n is negative? What are we gonna do about that, right? I mean, the obvious was, the positive was a little bit more obvious, just, but if it's like 3 times A, just add A to itself 3 times. What if it was negative 3 times A? How about that? Here's another way to do it. Oh, yeah. Or, right, just add A to itself n times, absolute value n times, and then take the additive inverse of that. With this definition of how to act, right, take an integer n and follow this rule here, any abelian group is a Z module. And so this kind of completes this is what a generalization of. If you have the ring as a field, then this is a vector space. If you have the ring as the ordinary integers, then this is just an ordinary abelian group. So that's kind of generalization. Let me give you some other rich examples. Let me give you a collection of examples here. I like examples. Let's see 0, 1 be the set of F 0, 1 into the reals such that F is continuous. So just take all continuous functions on the interval from 0 to 1. I was going to say we learned, I don't know if you learned it or not, but you were probably told in calculus that this is an abelian group. Only, I bet they didn't use those words, right? But one of the things that they did say in calculus is if you have 2 continuous functions and you add them up, it's a continuous function. And also they probably said something else. If you have a continuous function and you multiply by a real number, a scale, then it's still continuous, right? And so from this you get essentially that this thing is an abelian group, right? Add 2 continuous functions to negative. This is an abelian group. And in fact, this is a vector space over reals. And in fact, it's a vector space over Q. Right? Because what happens when I multiply a real function by Q, that's still a real function on 0, 1. Everybody agree? So it's a vector space on a smaller field. This is a module over Z, because after all, it's an abelian group. It's actually a module over this set of elements A plus B radical 2, where A and B are integers. Because this is certainly contained inside, the reals, which is contained inside this. So this is, this actually, this module is very big. Do y'all remember doing direct sums and direct products and algebra, where you talk about the direct sum of rings? One of the cool things that we'll find out about free modules, which in particular encapsulates all vector spaces, which is vector space overall, is, so this is kind of a spoiler, so I hope I don't ruin the whole movie for you. But as an R module, well, let me say R vector space. This is isomorphic to a bunch of copies of R. How many? Ooh, I don't know, a lot. Right? Well, that's one of the cool things we'll find out about vector space. When you have vector space over a field, so this is what's for, if you have any vector space over a field, I don't care what it is, any vector space over a field as a vector space will be isomorphic to a direct sum of some number of copies of whatever field you're over, which is really cool. As a Q vector space, this is isomorphic to some number of copies of Q. A lot more copies here required because every one of these is uncountable and each Q is countable, right? But that's really cool. As a Q vector space, this weird old thing that I came up with out of calculus, as a vector space over Q is the direct sum of a bunch of copies of Q, period. And over R, it's a direct sum of less, but still a lot, copies of real numbers. So that's something to look forward to. Here's another important class. If R is a ring and I is a left ideal of R, then I is a left R module. So you can either leave the words left in for both of them or remove them both. For my example, I'll remove them both. I like commutative rings. Take any ideal inside a ring, any ideal. First and foremost, that ideal is an abelian group. Ding, 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 first thing for an R module, right? What else? An ideal sucks. It's a vacuum cleaner. When you multiply anything in R times anything in I, it's in I, right? And there's your scalar multiplication right there. So when you multiply something in R, something in I, it's in I, and that basically gives you your R module structure. So that's an important class. So in other words, modules generalize ideals. Yes.
For the first example, so if it is a vector space, then it is a R module.
Yes, any vector space is an R module, but the converse is not necessarily. Mhm.
So in this example, I is functioning as the ideal is serving as the abelian group, or is the ring?
Yes. Yes, I is the module, it's the abelian group. And the multiplication, the binary operation is, and because of the fact this is an ideal, this is actually is in I, which is what we need. I should give you an example here that kind of points out modules generalize ideals in one sense here, but you can have an R module that is nowhere close to being an ideal. So example 3, and this is a reiteration, but I do this to kind of emphasize, Z2 is a Z module, but not an ideal. Right? Because Z2 is an abelian group, and the module structure is basically you multiply an integer times an element of Z2, right? Well, every integer times the 0 bar is 0 bar, no problem there. And an integer times the 1 bar is 0 bar if the integer is even, and 1 bar if the integer is odd. But Z2 is nowhere near being an ideal. In fact, Z2 is a finite group, and the only finite subgroup of Z is the identity. Here's another example. If R inside T are rings, then P is a left R module. And if the rings are commutative, then I can throw out the left business. Right? Because notice, since R is a subring of T, then anything, when you multiply anything in R times anything in T, is still in T. Right? So again, that's another kind of wide class of modules. Any ring containing a ring R is a module over the ring that it contains. Here is an exotic example. I like this example quite a bit. And we're actually going to use this example later in the course to kind of deconstruct canonical forms of a matrix. But this is kind of a neat example to show you that it's not all just, oh, look, you know, it's like everything seems like, oh, well, I've seen subrings before, and I've seen this before, and I've seen that before. Here's one that's a little different, I think. Let F be a field and V be a vector space. Let F be a field and B a vector space over F. Suppose T is a linear transformation from V to V. You all remember linear transformations from the old days and in whatever course that was, which in semblance therapy. By the way, that was one of the things that we had about linear transformations and linear algebra. What does this say? This means it's a homomorphism of billion groups, right? Which is kind of cool. So we see that connecting back. There was also something else for linear transformation. Anybody remember what it was?
Scaling.
Yeah, you can suck the scalar out of the multiplication, right? So like T alpha V was equal to alpha TV. And here B, W are in V and alphas in field. Okay, so suppose I give you a vector space V over the field F, and I've got some linear transformation T that goes from V to V. So we can use E to make V a module over, okay. V is already a module over F because it's a vector space, right? That's what we said, it's a vector space over this. But I'm going to make this a module over F of X. Right. So how am I going to do? So I know that there's a way to multiply scalar times something in the vector to end up in the vector space. That's what the scalar multiplication is. But how in the world am I going to do it with a polynomial? Right? So let's see. see, if f of x is in a polynomial over the field, and b, well, I'm gonna, b is in b, I'm gonna put a little hat on it. Anybody want this? Anybody want to guess how we can use that polynomial, multiply by b, and get something else in b out of it? Now, I'll give you a hint. I did say we're going to use t something.
So if you have like an x squared, do you just use the linear transformation twice?
Okay, that's, I think you got it. So what I'm going to do is f of t of v. So let me give you something abstract and then maybe something more concrete. So let me kind of show you this in action. Suppose the polynomial is this way, then I am going to what do I mean by plugging in t to this? Well, and I've got to do something with that alpha zero.
Right, then.
Okay, good. The appropriate size identity matrix, or the identity transform. I mean, this could even be an infinite dimensional vector space, perhaps. But the identity function. And notice, since t goes from v to v, t goes from v to v, so t squared goes from v to v as well, and so forth, so on. So all these make sense. So when I do f of t of v, this is plus alpha 1 t plus alpha 2 t squared. V, which is, well, this first one is just going to be alpha 0 v, right? No problem there. This is alpha 1 tv plus alpha 2 t squared v. So this is t of v, alpha k dk v, which is in v. So that is an interesting way to make an R module, right? But because of the fact that t is a linear transformation, you should check that this actually is a module. Certainly, we already know that v is an abelian group, right? That was given to us right out of the gates, right? But it's easy to see because let me not run my mouth like that. Let me actually put my money where my mouth is, at least a little bit. What do we have to satisfy? Well, if you look at, you need to show that r times x plus y equals rx plus ry. Both sides. So let's take this out. So let's consider f of x times v plus w. Right? Well, this is f of t operating on v plus w. But remember, the whole of f of t is a linear transformation, so this whole thing is a linear transformation. Everybody agree with that? So I could go through and do the separate things, but remember, f of t is actually a linear transformation. So this is f of t v plus f of t w, right? Which is f of x operating on v plus f of x operating on w. So there you go. And the others are similar to this, right? So there's a little bit of my labor about this. Any questions on that? So it's kind of a neat example of a module. And like I said, we've got application. We'll do some applications of this soon. Let me give you another important example. These modules are called free modules. Anybody remember what's one of the big theorems about vector spaces? You know, you hash this a little bit out and later out, but any vector space has a environment. From a computational standpoint, you use this quite a bit, right? Any vector space had a linearly independent spanning set, which is a basis. That's right. Any vector space has a basis. That is actually going to be one of the striking differences between modules and vector spaces. It's where vector spaces win, they're more powerful. Any vector space has a basis. Modules, not always, but there are types of modules that do have a basis, like a vector space does, similar. And these are called free modules. And here's what they look like. And we'll look at these definitely in depth later. This is kind of a good example. If R is a ring, well, let's actually, you can generalize this, but I prefer to stick to it. This notation for me means commutative ring with identity. Right? So if R is a commutative ring with identity, then the direct sum R I in some index set is an R module. With multiplication given by let's see, AI. Here we'll have R and R and AI in the direct sum. R times this net of AIs, it's just the net of R AI. So you just slide that thing right in there. Right. So for example, if you had R equals Z and then Z sum Z sum C is a Z module. With multiplication given by K times ABC is KA, KB, KC. This is a very important class of modules. This is called a free R module. And we'll talk about these later. And actually we'll discover that one of the fundamental things about these kind of modules, the free ones, is that any R module is the homomorphic image of a free one. So that's another spoiler for later. But hopefully these examples, just think of modules, they're sort of vector spaces over a ring, generalized abelian groups, generalized vector spaces. Any questions on any of this so far. Yes,
Is that A subscript I?
it's a subscript. Yes, it's a subscript. Yes,
And then R is an element of the first, or like.
yes, R is an element of this animal here.
Oh, okay.
Others. Okay. Well, you all have a good one, and we will see you on